In the third part of this sequence of talking about channel flow, I want to spend just a couple minutes talking about two concepts. One is the mean velocity of a fluid, kind of what's the average or the mean velocity of the fluid in a channel. And the second is to talk about the discharge, that is how much fluid comes out at the end of the pipe. And we might measure that as a quantity of the volume of fluid per unit time. That if I have a bucket and I have my hose, how quickly am I filling up that bucket? What is the volume of fluid per unit time? So those are the two concepts, and we're in position to make some progress on talking about them. So here's the case of a stream. And again, the details of this Chris will work out in a separate video. But what we want to do again is we want to talk about the discharge. And the discharge is again the volume of fluid that comes out per unit time. And it can be written as the area of the channel, the cross-sectional area, shown schematically here of the channel, and then times the velocity of the fluid coming out. But the question that we're confronted with is what velocity should we use? We've just seen that in the channel flow analysis that the velocity at the top of the fluid can be quite fast, but the velocity at the bottom is zero. And if that's the case, exactly what velocity do we use? And the answer to that is we use what's called the mean velocity calculated for the fluid. So we need to calculate the mean velocity, and from that we can calculate the discharge. Okay, so the mean velocity is defined here. It's just equal to the integral of the velocity over the height of the channel, over the position in the channel. And then you normalize that by the integral of the height of the channel from 0 to h. And that allows for the possibility that there might be variations in the height of the channel. And we'll do it for a simple geometry, the one that we looked at early on. And I'm going to do it for the case where we have a pressure gradient, where we worked out the relationship between the velocity and the vertical height. And we'll calculate that mean velocity. And we could do it for other geometries, but this one will serve as an example, and you'll be well equipped at that point to do others on your own. Okay, so here we go. So we're going to switch over to the white panel, the whiteboard, and we're going to try to calculate the mean velocity. So we want the mean velocity, and from that, we'll calculate the discharge. And we said the mean velocity is just the integral of the velocity as a function of vertical position, x2. We want to integrate that over the height of the flow, dx2, from 0 to h. And if I were to ask you about, is that enough? Is that dimensionally correct? You'd say no, because here on the right-hand side, we have velocity times distance. On the left-hand side, we just have velocity. And so what we need to do is normalize that by the spatial position in the vertical direction. So we're going to integrate that, dx2, from 0 to the height. And we had the expression for the case where we have flow between two fixed parallel plates. It's going to be the integral from 0 to h. And that velocity just looked like 1 over twice times the viscosity times the pressure gradient, dp with respect to dx1. All of that's constant, so we can take it out of the integral. And then we had the spatial dependence was x2 squared minus h x2 divided by h. All right, so h comes from this integral. That gives us the h. And this is the velocity that we had set up. And you go back and look at the PowerPoint, you'll see exactly that expression for the velocity profile. So if I plug that in and I do the integral, this ends up looking like 1 over 2 times the viscosity, pressure gradient, times x2 cubed over 3 minus the height h. And the integral of the second part gives me x2 squared over 2. And I have to evaluate that between 0 and h. And this is all divided by this h that we had here. Okay, and if I do all that, you can see when I evaluate at 0, I'm going to get zeros, so those are going to fall away. And so the only place I'm going to be left with something is when I evaluate at the bottom surface. So this is 1 over 2 viscosity times the pressure gradient, dP dx1, times h cubed over 3 minus h cubed over 2 divided by h. And if I've done all of that correctly, I'm going to end up with the mean velocity is just equal to minus 1 over 12 u times dP dx1 times h squared. So something that should catch your attention right away is that there's a minus sign out here, and I have a velocity. Does that mean the velocity is flowing the opposite direction? Well, I'm not going to answer that question for you. I'm just going to let you think about it. But there is a question, why do I have a minus sign here? And can we understand, is the flow really going in the right direction? All right, and from there, I want to calculate the discharge. And the discharge is simply, we write as Q. And we said that was the mean velocity times the area of the channel. So that's the cross-sectional area of the channel. All right, and so the mean velocity in this case is going to be Q is just going to be minus 1 over 12 times the viscosity times the pressure gradient times the height squared, and then times the area of the channel. Okay, so that's the discharge. It tells us how much fluid comes out. So it's the volume of fluid per unit time. All right, let's go back to the view graphs for just a second. This is what we've calculated. We've calculated the mean velocity, determined the mean velocity as a function of the constraints on the system, the viscosity of the fluid, the pressure gradient, how hard we're pushing, the height of the channel. And then from that we can calculate the discharge as just the mean velocity times the cross-sectional area.